thing about the 6.7 gigahertz level laser observation, like the monitoring project. So my research is all about the time domain thing. So let's get it started. This is a little context to give a brief thing. Like I'll give you a little introduction by my about the background, and next I'll give some introduction about the TMRT laser monitoring project, which is Chinese laser monitoring project, and third part is talk about some results, recent results, like case studies. Next one is our recent work with Prof. James and Gordon about 33 years of laser vibration. So finally, I'll give a little summary. So first of all, just to give a little introduction about the thermal lines and the laser lines. There's a little difference between thermal lines and laser lines. Like if it is a thermal line, the distribution of the energy, the population of different energy levels is gonna be a pyramid. Like with higher energy level, the lesser the population. But for laser lines, it's gonna be a little bit opposite. So for certain energy level, they can observe the energy from the outside. Maybe it's irradiation, maybe it is collision or something. And they can very effectively pump the molecule to a higher energy level and let them stay there for relatively very long time. But the higher energy level is pretty unstable, so with a little bit interrupt, disturb, or fluctuate, it's gonna come up to the more stable energy level. So during this process, it's gonna release a lot of photons, release a lot of energy. So the laser line gonna be very strong, very narrow, and the laser spot is gonna be very small. And the relationship between like the main objective we are talking about today is the methanol lasers. And talk about when it comes to methanol lasers, is a very excellent tracer of the high mass star formation regions. And because the high mass star formation region provide a very compact and high temperature and very molecular dense environment. It's a perfect condition for exciting the laser transitions. So methanol lasers are there are two kind of methanol lasers. One is class 1 methanol lasers. It's like the picture shown here. Class 1 methanol lasers are mainly pumped by the collision. So they are always typically tracing the dynamic structure like outflow, jets, and shocks, something like that. So it's a little bit far away from the central protostar. But for class 2, another methanol lasers, class 2 methanol laser. This kind of a methanol laser is mainly pumped by the infrared radiation. So they're usually very close to the central star. It's very good and very sensitive to the changes of the central protostar, like radiation field, like magnetic field, something like that. So there's already some excellent work about the variation of a 6.7, which is the strongest class 2 methanol laser. monitoring project, and there's also some amazing result. Like the very first accretion burst source, S255 IR, is a very famous source, right? So the 6.70 Hz methanol like explode during the accretion burst events. In several months, the flux density of the methanol increased like over 1,000 times, like 1,000 times stronger. So also we can see some flow image change. Like, so the accretion rates get higher, so the flow gets stronger. And there are some other examples like G358. This is also a accretion burst source, and I forgot the picture. Sorry. The flux density of the 6.7 gigahertz methanol increased like very rapidly, also in a few months. And they also used the interferometry to observe the major spots during the increasing phase, during the bursting phase, and they found that the major spots like moving outwards as the flux increase. So it's like the central protostar is creating a heat wave and propagating outwards and light up the major spots.
Hi, Shimin.
Yeah.
Sorry for interrupting. Is it possible to use the laptop microphone instead? Because it seems like we're struggling to hear you with your earphones. Yeah. Try to use the laptop.
Okay, I'll try. I'm sorry about that. How about now?
Try to say something.
Can you hear me?
Nah, it's the same. Try again.
Oh.
Okay.
Oh, I'm sorry. I chose it wrong.
Okay.
Can you hear me?
Yeah, I think now is much better. It's clear.
Really? Okay. I'll just continue.
Okay, cool. Sorry for
about that. So if you put all this observation data together from different epoch, the major spot's gonna form a spiral arm shape like structure, which is might suggest there's a accretion disk. And also there's another source like NGC 6334I. I don't have to introduce this one because we have already read the paper. It's also a accretion burst source, big burst here, and also some continuum image change. And this recent work, our recent work, like the G36, this has also shown very rapidly changing of 6.7 gigahertz methanol measure, but also the OH measures. So this kind of also might give evidence for something like after the accretion burst, there's might be some magnetic reconnection process happen here. So with all this kind of amazing source, amazing results, we can see that the measure vibration traces all kinds of accretion or accretion events like the accretion burst, heat wave, and the magnetic reconnection. So we started to use a telescope to monitoring project. Of course, there's already some big project for monitoring measures, but you can never get enough data, right? So the more the merrier. So we use TMR radio telescope, aka TMRT, and it's located in Shanghai, China. It's a very big telescope and it's very powerful. So it's very effective to use this kind of equipment to observe the 6.7 gigahertz methanol measures. So where does the sample come from? This sample is come from our another work. There are about 2,000 methanol measure sources in the Milky Way, and because this kind of 6.7 gigahertz methanol measure is mainly pumped by the infrared radiation, so we cross-match the sample to new WISE database, so to identify if those sources are made infrared. There's some infrared vibration for these sources. So we found about 540 sources have considerable made infrared vibration, but not all of those sources are observable to TMRT. So there are only about 200 sources are observable to TMRT. So we select those sources to monitor. And here shows some results, primary result, like we can observe very faint sources, and there are also some variations for those faint sources, even some periodic sources. And because our sample is selected from a new WISE database, so you can see some synchronized variation between like mid-infrared emission and maser flux. But unfortunately, the WISE satellite went down completely, so there's no new WISE data anymore. But we can still use some other method to confirm this variation. So with those data, we select some interesting source to give some detailed analysis. Like this is the G353 is a very interesting source. Like there are lots of methanol thermal lines inside of this kind of high mass star formation region, and also the shape is very, I don't know, unique, because it's almost perfectly face on to us. So we can see this one is not a accretion disk. It's a methanol envelope. But this little hole in the middle, this is accretion disk, because the accretion disk is dusty and compact, so it's optically thick. You cannot there's barely emission from this area. And this methanol envelope has a rotational structure, and it's also gravitationally unstable, so you can see some info structure in it. So it's like a candidate of accretion burst. So the bigger picture of the source is it's like this. It's almost face on, but a little bit offset from line of sight is about 8 degrees, and also there's a accretion disk, there's an envelope, so we can study the structure of the disk, the envelope at the same time. And also, because it's slightly offset, we can also study some like a jet structure or outflow structure. So on the left panel, on the left picture is the TMRD data. So you can see the spectral line. We have identified 3 Gaussian feature, but the strongest one is at like 4.5 kilometer speed. And this is the light curve. You can see there's definitely something periodical of this source. And to find this period, we use the Lamskago program to give it a test. So the result is about 320 days. But you can see we only cover like 2 cycles data. So we use 2 previous data point to extend time range. So finally, the period is about 330 days. But this year, the Japanese published an article to confirm our result. They have used 13 years data, and the period is gonna be 310 days. So they got more data. So I think their result is more solid. We also found some other evidence about the vibration. We have used 2 epoch of ALMA data. One is during the sources fading away. One is for the sources bursting, some kind of this situation. And when we analyze the methanol thermal lines during the fading phase, we can see there's part of transitions. We can use it to calculate the rotational temperature, but there's still some transitions you cannot use. But if we look at the bursting phase data, there's no like a pattern for those distribution of transition lines, so we cannot calculate a reasonable temperature. So we assume because this is a fading phase of the star, of the protostar, so the LTE, so it's under LTE, but when the protostar is bursting, the LTE situation is like destroyed by the source heating up the area, the surrounding area. Also, the Japanese found some evidence for there's a synchronized vibration between the mid-infrared, which is neowise data, and the maser emissions, the maser flux. So we can barely confirm this kind of vibration is coming from the protostar. So this protostar is like it's like a heart. It's posing like a beating heart. Every time it pulls, created like a heat wave propagating from the central star to the outside, and heat up the area it passing through. So when after it passing through the gas back to the LTE condition. So that is why we can see those non-LTE or and LTE at the same almost at the same area, but for different time, of course. But there's still another possibility, like there are also a binary system inside of this region, also can create this kind of position like pattern. So this is just a little summary for G353, and the next one is G35. This is also a very famous source. You can see here's a little bit straight filament structure for this region. And the high mass star formation region is about here. So you can see there's a core A and a core B. And what is interesting is for core B, there's a binary system. See, this is like a accretion disk or something, and there's a rotational structure, and there's two sourced here. And for this source, we combine our data to the AMAT program data, but we don't have the original data, so we just analyze the aeration a little bit. We cannot analyze any other stuff like with the line width or something else, or velocity shifting stuff. We don't know that. So you can see this feature. These are 12 features in the spectrum, and the feature 4 shows a very clear periodicity, but the others just not that much clear. So, but you can see the methanol measures tracing both cores, right? So we want to try if the methanol line is still tracing the variation of measure lines. Methanol thermal line is still tracing the measure line. So we identified some lot of methanol thermal lines here to calculate the temperature. You can see this fitting result is very good actually. So for core B, which is the periodical stuff, like possibly periodic stuff for periodic core, the temperature is tracing the variation of the measure, and also for core A, still tracing the variation. But if we take a look of the new WISE data, it's something weird. Like for core A, is kind of synchronized. Like the blue line is the new WISE variation. No, sorry, no. The red lines is the new WISE variation, and the blue lines are the flux of a measure. You can see this in the middle part, they are synchronized. But if you take a look of the core B results, it's gonna be anti-synchronized. This is the opposite. So the core A is mainly affects the entire region and cause this mid-infrared variation, but the measure lines, the measure emission is tracing like a very local stuff, like the variation of the core B and the core A is different, right? So this is a little summary about G355. The last one is G351. which is also a very interesting source. There are multiple continuum compact source here. At least there are 9 star forming here, and the 6.7 gigahertz metal matrix tracing area is about here. So the MM1 is here. So this area we also found there's also some research shown that there's a H2 region here. So this is definitely a high mass star forming here. And in 1996, Gordon had published a paper to analyze the maser vibration, and they noticed there's velocity shifting. No, there's several maser flares, and there are several maser flares, and during the maser flare, there's velocity shifting from the red side to the blue side. It's not a straight, it's a little bit climb. So beside that, with the new data, we find that there are two new features here, but unfortunately the previous data doesn't cover this speed, this velocity, so we don't know if this is entirely new, but those two features are new, reported here. There's no previous paper talk about these two features. So these features may be about to appear in at 2001. So this is like the spectrum from before 2001, and the orange one. I don't know if this is orange. Is the spectrum after 2001. There's apparently two new features here. So there's something more. Like actually this especially for the two new features, they are kind of they're kind of episodic. The variation is kind of episodic, like the dots to dots. When we see this kind of thing, it's like initially we think about this as whether it's periodic, but it's very weird because this is not evenly distributed. So we Prof. James and Gordon suggest that there might be more than one period in the source. So we tried to figure out whether there's a multiple period inside of the source. So if we use like the typical Lambda-Skagel program, we only can detect a stable period like across the whole time. But what if the period is just short-lived, like they only exist in a very short time window? So to examine this kind of period, there's another tool we can use is the wavelets. It's the wavelet. But to use this kind of strategy or method, the sample frequency must be very even. So you gotta observe the source every one day, or every 2 days, just evenly separated. But to do observations, this never gonna happen. So there's another tool we can use is the weighted wavelets Z transform, the WWZ. It's basically wavelets, but you can the program use different time window to move through time to see which period have higher power. So this is basically the result. But here we only take like the top 30% power as a reliable result. So we do detect some multi-epoch in this source. And for those results, we take those results as an initial guess or something, and to perform like a feeding to the original data. So this is the feeding function, and this is the feeding result. You can see this feeding result is not very good, but it shows the variation of the variation trend of Maser flux. So we only consider the result that is confirmed by only accept those periods confirmed by the LSP Lamskago program here, and the WWZ, like the top 30%, and the feeding result as a more reliable period. So we detect at least 2 period for each feature. Like the feature minus 2.5, we've detected about 800 days period, and 1,300 days period, something like that. Because you can see from the recent 10 years, especially for those two negative features, it really is 800 days period here. But for those, there are also some like very long period, like 4,000 days or 5,000 days or even more. We don't take this as secured result because this period is even very long for 33 years observations. So those we only detect like less than 2 cycles of variation. So we don't take this as a confirmed result, a more reliable result. I'm sorry. So so far we don't know the causes of a multiple period thing, but we can give some guess about it. Like there's multiple there are multiple models can explain the period of variations, like CWD, colliding wind binaries, positions, and eclipsing, and something like a periodic accretion. But every time I think about this, it's there's only one model for one source. But what if in the real case it's not like that? What if there is a binary system, and also one of or both of the stars is still opposing? So there could be some multiple causes for the periodicity. So to give a I'm sorry, I forgot how to say the word, summary, and so most of the methanol measures are varying differently. And no matter it's a strong source, it's a faint source, they're all varying. They're all like show different kind of a fluctuation or variation. So the native cloud environment can trace this kind of information. It's not like only major variations. There also can be some methanol, some thermal lines condition can trace this kind of thing. Even some continuum emission also can trace this kind of thing. And this kind of variation can caused by different reasons, like different sources. There could be multiple like protostars inside of one star forming region. So those measure spots can be affected by different protostar, and different protostar have different variation, patterns, right? And the periods may changing through time, right? So based on this, we have something to think actually. There's about 2,000 masers inside of the Milky Way, but there are only about 40 periodic sources have been reported. The ratio is about 5%. It's very low actually. They already have some very long monitoring project, but most of those sources are not showing very clear periodic variation pattern. So maybe this is because some of those sources are not have unique, like a single one period is a combination of periods, multiple periods. So that is why we didn't report many periodic sources. So maybe we should really take a look back to those sources and whatever it is, period or non-period. There might be some more period in this kind of source. And another scenario is the multiplicity. There's more and more research reported the high mass star formation process is the high mass star formation region is multiplicity system. So the major spot or those variations may be affected by the multiple cores. So this is all my presentation. Thank you, everybody. Any questions?
Thank you very much, Shimin. Any questions? Yes, Jude.
Thanks, Shimi, for the nice presentation. I have maybe 2 or 3 questions. The first one is, how did you confirm that that core B is a binary system? The core B in G35 is a binary system. How did you confirm, or is it by visual inspection?
This one?
G35.
Oh, this one.
Yes, you
right?
say core B. Yes, this one.
It's not. I didn't confirm that. I don't confirm that because there's already a research talk about this. There are 2. You see, there's 2 cores here with a higher resolution. This is a jet melt, and there are 2 1.3 centimeter compact thing here, and in a one kind of a rotational disk structure here. So they think there's a binary system here.
Okay, it's just a prediction that it's likely a binary system.
Yeah.
Okay, thanks.
It's not a prediction. I'm just putting the link to the paper.
So in 2013, Sanchez Monge used ALMA data to show that there is a second binary Keplerian disk in that object. I'll put the link in the chat.
Oh, great.
Okay, thank you, Prof.
Thanks. Okay, secondly, for G353, did you look at high sensitivity data like Meerkat to confirm that there is no H2 region?
Yep, there's no H2 region here, especially close to the central protostar. There's no H2 region.
Okay. Okay.
Did you check Meerkat data?
Yeah, I checked.
That's what I asked.
Okay, cool.
The emission is very far away from the central protostar.
Okay, okay. Maybe you can discuss that later. The last one is G351. Has it been reported to be a periodic measure? Periodic methanol measure.
I'm sorry, I didn't get your question.
I mean G351.
Yeah.
Has it been reported to be as a periodic methanol measure?
Yeah, no. There's no evidence so far showing that this is before. This is a periodic measure source.
Okay. Thanks.
Thank you.
Thank you, Jude. Rahul?
Hi, Dr. Shimin. Very nice talk. I just want to know on the right panel on the top, is that a maser flare of multiple methanol masers in the G35 one?
I'm sorry?
I just want to know on the right panel, is that a maser flare of multiple?
No, this is a spectrum.
Okay.
Okay, thanks, Rahul. Next is Paul.
Good afternoon. Thank you for your talk. Just a question on how you did the fitting. So right at the end, you showed how you fitted G353 with 3 different periods. I'm curious to see how you managed to work out that there were three different periods in that source. So I think it's following the source you had towards the end. That was G53. Which was last slide 23.
Okay. This one?
351, not 35.
Sorry, it's 351. My apologies. Sorry, 351. Because if you look at the data, it's very difficult to try and determine what is happening. You're seeing multiple sort of flarings or increases in intensity. How did you manage from that to deduce their 3 different periods and then go about trying to actually fit the data? Because the fit is remarkably good.
Yeah. Thank you, Prof. Paul. Yeah, this is we take this result as a very initial guess, especially for it can tell the active years. You can see here. So we added I added this is a window function. So those multiple period only are fitted during that. The specific period are only fitted for specific time window. So that is why there's fitting fairly well. I don't know if this answers.
No, that makes sense. And that if you actually show the fit across all the data you have, does it look as good, or there are areas where it doesn't seem to work?
No, if you fit all the data, it's gonna look.
Okay, so that says why you think that the period might change. So you might have a certain period for certain times and not for others. But it does look like we've lost Dr. Song.
Yes, I
To
think so.
wait to see if he comes back. Welcome back.
I'm sorry, I don't know what happened. I'm sorry.
No problem.
Prof. Paul, can you continue?
I was going to say, in terms of the data actually fitting only on some periods, and then you said if you try to fit all the data, it doesn't fit for other periods. Is that why you think the period changes? So you have a certain period that holds for several years, and then it seems to vary after that.
Yeah, yes, it is. And you can see from this WWZ result, the period doesn't last for a very long time. There's no like a very stable period here. But for a certain time window, there is something like a peak, like here, 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 and here, something like that.
Okay, that makes sense. I was just very curious about the fits, and because the data you showed seems to fit incredibly well.
Thank you, Prof.
Thank you very much, Paul. Next is Prof. James.
Thanks, Shimin, for the nice talk. Did you have a look on whether there is a VLBI map of the mesas of G351?
Map?
Yeah, okay. That's 351, yes. Is there any ALMA dust continuum, a high resolution dust continuum image of these objects?
Oh, the background is ALMA data.
But it says VLA.
No, those blocks is VLA result.
Yeah. We probably need something higher resolution to resolve the cores, to see how many cores are in the region.
Yeah.
I would suspect there may be 3 objects in the region.
Here?
Yeah.
Okay.
Maybe that's what is causing this problem with the periodicity.
Yeah, I think so. Yeah, thank you.
Yeah.
Okay, thanks, Prof. Jonas?
Thank you, Shimin, for the nice presentation. You have presented both thermal methanol line and the mesas. I didn't get whether there is a direct correlation between the spatial distribution of thermal gas and the methanol emission sites.
I'm sorry, I don't get your point. Which figure are you referring?
I think it was panel. It was slide number 10, panel A.
Maybe you can come to me and we can talk about this.
Let me check.
Assuming he wants to know whether the thermal methanol line has special coincidence with the mesa lines.
thermal line?
Yeah, if the
Oh,
thermal
the
line
flux of the
and
thermal line.
yeah are positionally coincident with each other.
Yeah, actually, we tried that in this source, but it does not looks good. There's no clear clue that shows the thermal line, the intensity thermal line is varied, like with the mesoline.
No, not
We tried that.
variation. I think he's thinking about the position. You need to make the map
Yes.
of the thermal line
Oh,
and then plot the
Yeah.
meso position on it.
yeah, that is why we use like a specific features. It's not like in the integrated flux density. You see the feature 4 is basically here. So it traces the core B, and the feature, which one? Sorry, the 12 is here. It traces the core A. So
Yeah, but in this case, the background is continuum, right? Dust
yeah,
continuum.
continue.
So if you replace
Yeah.
the background with integrated intensity map of methanol thermal line and then plot the mesas on top.
Okay, I got you.
So he asked
Thank
whether mesa will be the same.
Yeah. Yeah.
Jonas is essentially
So
the same, I think.
Yeah. I was thinking that whether we can use that information maybe to trace the source which is causing that variation of mesas.
yeah, we are, because this is students' work that I supervise together with Professor Chen back in Guangzhou University. So we're doing this kind of thing, like image the methanol thermal lines, maybe like a moment 0 and a moment 1, 2. So we're doing this, but there's no like a very good result now. But the analysis is still ongoing.
Okay.
Thank you.
Okay, thank you.
Thank you, Jonas. Any more questions? Shimin, I have a small question, a simple one, I think, on page 11. Yeah, there's just something I didn't get. So the top right one, you mentioned that the accretion disk is the tiny white part, right?
Yeah, it's not Y1. There's nothing here. Like there's no. This is methanol thermal line radiation. So there's nothing here. There's no. Maybe there's some emission here, but it's optically thick.
So yeah, that's also another. So okay, that answers part of my question. I thought the tiny white part is the disk, is what represents the disk. So could it be that the gas and dust there is also cleared by a jet, so there is no emission from that part, and it's not as a result of optically thick central part? Is that a possibility?
Yeah. It's you mean because of the jet or a flow?
Yeah.
So it looks like a blank here. I'm sorry.
Yeah, that's what
I understand your question. I'm sorry.
It could be a cavity that's asking if there is a plowed cavity there.
I don't think so. I don't think so. So there's another image. You can see the flow is like to that direction. You can see it very clear. So I don't think this is a cavity stuff. It's not like a right into your face. No, this is slightly offset from the line of sight.
Yeah, it looks too compact to be cavity. So
The compact nature tells you might be the continuum source absorbing the line.
Okay.
Yep.
Okay, thanks.
I think if you plot the continuum on that, the continuum will fully close the gap, and that's how you easily know it's just continuum source absorbing. Yeah, you can see. Oh, there is actually contour maps here. So
yeah.
Okay. Yes, Rahul.
I just want to know what affects the periodicity. Like Prof talked about something affecting the periodicity when he mentioned the VLBI maps of this of G35. I'm just curious to know what affects the periodicity.
Sorry.
I just want to know what affects the periodicity.
I don't really get your point. Could anybody help me to understand the question? I'm sorry.
Raul, what do you want to know? Is that what affects the periodicity?
Yes, when you talked about the VLBI map and stuff, I think you said something that affects the periodicity, which I didn't get.
No, so the VLBI map is to show us the positions of the masers. So if you have the positions, you know which object it corresponds to, and then which object is behaving in a way as to make the light curve of the masers to show periodicity.
Yes, it is. Like this source, you can see this dots or major spots actually. These dots are major spots. There's a multiple major spots along this line. So you can see these features for different velocity. They show different vibration pattern. Some of them are apparently periodic. Some of them are not. So it depends on which source is mainly affecting this kind of major spots.
Thank you, sir.
Thank you, Rahul. Elisef.
Hi, Dr. Shimin. Thank you very much for a great talk. Can you please go to slide 12?
12. This one?
Yes. You mentioned something about using 2 data points to extend your time ranges. So I wanted to understand which methods did you use to pick those 2 data points?
Just look into papers.
Or you just looked into the papers?
Yeah.
You didn't use any technical method to pick those data points?
No. This
Okay.
website, there's full of major stuff, so you can look for major information all the time in the website. You can just use it.
Okay. I thought maybe you used another technical method to pick those 2 data points. Thank you very much.
Yeah, thank you.
Thanks, Elisep.
You're
Before
welcome.
I give another chance to Prof. James, Shimin, on, I think it's at slide 16, where you 16. Have the VLAs. Yes. Where you have the VLA A, VLA B, VLA C. The central one does not have centimeter emission. Is it because it's a very young source? Not this one. I think it's 16. Is that 16?
16?
I think it's.
Which?
No, not this one. I think there's a. Okay. Let me. You discussed it just before this one, before Elisep asked the question. I think it's.
This one?
353, I think.
I think it is G351 or something. G35 or something.
351, yeah, maybe.
351, I think. Yeah, so where you have VLA 2C, is that the core or that is the other square? VLA 2C. So where you have these arrows, there is no centimeter emission completely. Where you have the blue and the red arrow showing the outflow, I think there is no centimeter emission associated with it.
centimeter emission? You mean here?
Yeah, around there, around where you think the core is. Yeah.
Yeah, 'cause this.
That's 2B. That whole area is the 2B, and if you look at the zoom in, you'll see
Yes.
that's the view in the 2B.
Yeah.
Okay. So that the whole of that is 2B. Okay.
Yeah.
Okay. Initially, I thought 2B is a separate source, so that there is no centimeter emission. I was wondering how young the source is. Okay, Prof. James, and then Paul.
So, Shimin, I'm keen to know what your opinion is on finding a hybrid system that uses both the WWZ and Lomscago to do periodic mesa fitting. Do you think that is possible or something that would be sensible?
I think it is. I looked a little bit into the WWZ programs, like it's using different period of time window moving through the time to see if this period have a higher function power for a specific time. So it's very, if you can find a peak in both like a LSP Lomscago program and the WWZ, I think it's a very secure result. I think we can do that actually.
Yeah, cool. Okay. Thank you.
Paul, please.
If I can go ahead.
Yes, please.
Yeah, please,
I'm
Paul.
Curious just to get your comments or your thoughts on what, in your view, is the mechanism or cause of the periodicity. I know there are quite a few mechanisms put out there in papers. I was just wondering if you have any strong views after all of the work that you've done.
Yeah, it's a very hard question actually. Yeah, to be frank, sorry, I don't. It's very hard to think about the excitement process of the methanol of the masers and what is causing the variation of the environment. Maybe it's the molecule density, the gas density, and the dust density, and the temperature as well. But I mean, I'm sorry about that.
No, it was an open question. I think nobody has views. They have ideas, but that's about all. And I was wondering, you referred to a recent paper, that 2026 paper, where they looked at 353. You showed some of their graph where they had the 13 years of data.
Yep.
In the 2026 paper you have there from Hitachi on the right, just in that paper they had quite a strong view that it was the central protostar fluctuations or pulsations that were causing this period periodic behavior. Do you think their views and their analysis was reasonable? Because it's, I think, the first paper I've seen where they had fairly strong views as to what the mechanism might be.
Yeah, I think they make sense, and it's very personal stuff. Yeah, I think they make sense, and the data shows everything. There's no H2 regions, and the shape shape of the source is very unique. It's almost completely total face on. So the only a reasonable explanation is like the position. Yeah, but this is just some data shows that. I think they make sense.
Okay. No, thank you. Just no, it's something that we will slowly have more understanding as time goes by.
But I think there's like the G351, the multiple period. I think there's might be something more inside of the source. The light curve is not a very like stable one. They fluctuate a little bit. Maybe there's something more inside of the source. Maybe you can point to some other direction. Maybe there's is a binary system inside.
No, that's I think quite a valuable comment, because they fitted this and they showed their period to be quite accurate. But you do, when you look at the graph as you have the one showing at the moment, there is a fair amount of variability. If you looked at their fit, there was a couple of places where it didn't seem to fit that well. And I don't remember them commenting on what could be happening and why certain areas were not good fits. So I think your comment about potentially multiple mechanisms, multiple periods, actually is very interesting.
Yeah, thank you.
So these, I think these data sets are very difficult to try and interpret, and not nice and clean and perfectly symmetrical.
Thank you for that.
Thank you for the talk and the comments.
Any more questions?
Sorry, I just have a quick question for maybe for Prof. Yeah, my question is regarding the source G35, and apart from the paper that you shared, which says that they detected Keplerian disk on this source, there's another one. I think it's from 2017, where they also identified almost 4 continuum cores on this source. So I'm just wondering what really caused this breaking, or I don't know how I can say it, of this. Yeah. What caused this fragmentation?
Sorry, let me ask, are you saying in the region where Shiming is pointing now that they found 4 sources and not the 2 that we know, 8A and B?
Yes, they found they found 4. It's 2027 paper.
In what band?
They used ALMA. I think ALMA band 6. Let me quickly check.
I'll be very surprised if band 6 will resolve this into 4. Because I think this observation was band 7. Shimin, can you confirm?
Yeah, now let me try a little bit, maybe.
Yeah, so I'm looking at the link I shared. The observation there was done in cycle 0, and the band was 350 gigahertz. So that's band 7.
Okay. Even for in this observation, they also use band 7.
Oh, okay. I haven't seen that one where they use another band 7 and they found 4 objects.
I'll just drop the title here. Yeah, but what would be the cause of that, Prof?
Well, dust emission will always fragment and form various cores. So I think fragmentation will be one thing you can point to, but also if you go with higher resolution, you may start to find a find fragments in the disk. So it's not necessarily protostar, but it may just be a large fragment in the dusty disk of a protostar. So it could be anything, and I'm quickly trying to open the link you shared to see what it is.
Oh, this one.
I don't see any 2022 paper with this.
You mean this?
Sorry, let me check.
Yes, that one.
This, I think this is core A. So 1, 2, 3, 4.
Oh,
Yeah,
are you
maybe
referring to B? Are you referring to B1 and B2 and B3? Is that what you mean, Francisco? Francisco?
yes.
Yeah, you could find such thing. You can see that the B2 and 3 have only very low level contours. They may not necessarily be protostar. The only way you can say they are independent protostar is if you detect gas peaks, if you detect molecular line peaks on them. So yeah, for me it looks to be dusty fragments. If you look at A towards the south east, it was towards B2 in the figure with contour lines. You'll see that A seems to have a tiny core protruding towards the southern side, right? Towards B2. So it could just be a clumpy disk. Yeah.
Yeah, it's like this one. They refer it to like a jet note.
Oh, really? Yeah, I think that's what it is.
So is there more questions?
Any more questions? Seems like everyone is satisfied, Shimin.
Okay. Thank you.
Thank you very much for the nice talk. And we hope next time again, we request you to give us a talk. You'll be happy to. Thank you very much.
Thank you. Thank you, everybody.
All right, thanks everyone. And maybe a few announcements. There are a few deadlines coming up, including the Meerkat